today's physics club, we're extremely happy to have Professor Tracy Slatyer from the Massachusetts Institute of Technology. So Tracy's research focuses on trying to unravel the nature of dark matter using astrophysical data. And so she's very well known for a large number of key contributions in this area, in particular for the discovery of the Fermi bubbles. And so she's received a number of prizes, including the Rossi Prize, the Henry Primikov Award of the APS, and most recently the New Horizons Prize. And so today she will tell us about what the galactic center gamma rays can tell us about dark matter. So take it away.
All right, so testing first, can people at the back hear me okay? Okay, very good. And maybe if people on Zoom, if you could, I know, put a thumbs up or something to confirm that you can hear me okay as well, that would be great. So I've turned it off I've hit I'm not actually sure how to access that screen because I have got it on my screen here. So, yeah, sorry about this. Yeah, good. Yes, right. That's right. It's because it's sharing through this one. Very good. Yeah. Okay. Great. Okay. Okay. So it's not projecting from that laptop. Oh, interesting. Okay. But it goes behind but it's projecting from behind the screen and it's hiding. No? Okay, that is the wrong mouse click.
So I think now you should be able to, or no, while you're
if I push one.
Now click
Oh,
now it should.
We want to, I mean, I just don't, you think I should unshare or
Maybe.
Like, I mean, none of this appears on my screen.
Maybe just unshare.
I just unshared and then tried resharing and
share. Can you see? So where's this? Yeah, that's weird.
yeah, like I mean, I did have one come up and I already clicked that got it. So yeah, I am not sure how to access that particular issue. Like, I mean, that feels like it's sorry guys. It is not on either that screen or this screen. And if I go back to sharing, let's just play. It is now on all the screens. Oh, okay, excellent. Okay, the other mouse was what was needed. Very good. That's, you know. Okay, that physics insight having been demonstrated, let me begin the colloquium. Thank you very much for the invitation and for the very kind introduction, Ian. So I will try today to tell you some of the things that galactic gamma rays can potentially tell us about dark matter. I will not try to tell you absolutely everything that galactic gamma rays can tell us about dark matter, because when I tried to make an attempt on that, the colloquium rapidly got too long. So, but I want to start by telling you a bit about the puzzle of dark matter and why I spend all my time thinking about it. The first half of the colloquium, I'll be talking fairly generally about this question. And then in the second half, I want to talk more specifically about some work that I've done both in the past and in our work in progress on searching for heavy weakly interacting massive particles with gamma rays from our galaxy. And that earlier work was in collaboration with Ian Moult, right here, among other people. So I first want to begin by just talking about the puzzle of dark matter, and to make sure that everyone's on the same page, talk about the possibility of weakly interacting particles as a dark matter candidate, talk about how the dark matter would be produced in that case and what kind of signatures it would imply. Then I want to convince you of this statement: the gamma ray observations from our galaxy can constrain dark matter annihilation and decay across an enormous range of models, from subatomic particles to primordial black holes. Then, in the remaining part of the colloquium, I want to focus in on the question of, can we exclude even like really simple, really minimal, really classic scenarios for weakly interacting dark matter? And the short preview is that some of these are really hard to exclude by any means other than indirect searches, such as these in gamma rays, that there are significant theoretical challenges to calculating signals from these models, but we know how to handle those challenges now. We can predict the signals accurately, we can set constraints, and the answer is that for many of these models, we're either right on the border of ruling them out or they're already in tension with the data. Okay, now feel free to ask questions as I go. I definitely, if you're confused about something, put up your hand and let me know. And so let's get right to the big question, which is a question that motivates my research: is what is the dark matter of the universe? So things that we think we know about this puzzle is that there's some component of the universe that doesn't scatter, emit, or absorb light at an efficient level. That's what we mean by dark, but does have mass and hence gravity, which is what we mean by matter. I mean, really, transparent matter might be a better name. We don't think that this thing is sitting out in space absorbing light, but dark matter it is for the moment. We know a few other things about this component of the universe. We have a pretty accurate measurement of the fraction of the matter in the universe that it makes up by mass, based on looking at observations of the cosmic microwave background radiation, which was emitted when the universe was a few 100,000 years old and is the earliest direct light that we see from the early cosmos. From later times, we believe that the dark matter actually forms the invisible scaffolding behind a lot of the universe that we observe. These plots on the right are showing slices through a simulation of the formation history of the universe from the Illustris collaboration, which I am not a member, but many of my colleagues at MIT are. So these panels are running from early times at the bottom of the page to late times at the top of the page. And on the left-hand side, we're seeing this filamentary web of made of dark. So the left-hand side is showing the distribution of dark matter density over time. And we can see that it forms this filamentary web, sort of purple regions, and then later the white regions are regions of high dark matter density. And as time goes on, we believe that attracted by under its own gravity, dark matter collapses to form these dense regions. And the panels on the right are showing what the visible matter does in response. Because dark matter is most of the mass in the universe, the ordinary matter largely just follows its gravitational pull. And so we end up with regions of high gas density when the gas is attracted there by the gravitational pull of dark matter. In these regions, and these regions of high gas density are where stars and galaxies can be formed. So for every galaxy that we see out there in the sky, we believe that that is a visible tracer of a more massive skeleton of dark matter behind it. And simulations like these accurately predict the structures that we see in the universe today. Now, based on that, you might expect that around every galaxy, we should see high density of dark matter, just because regions of high dark matter density are the cradles of galaxies in the first place. That's what attracted the gas there in the first place. And indeed, that is what we see. This presentation is somewhat ahistorical. This was one of our first clues to the possibility that dark matter might be there before we could do simulations like the ones that I showed just a moment ago. So by measuring the orbital velocities of stars and gas clouds around galaxies, we can infer that in addition to the bright part of the galaxy that we can see shown in this cartoon by this little spiral, there is a large cloud or halo of dark matter surrounding almost all of the galaxies that we see, just as we would expect from this structure formation picture. But it's not just a prediction from simulations, we can also observe it directly. So these are all positive statements. These are things we think we know about dark matter, about where it can be found in the universe, about how it is distributed, about how much of it there is in total. But there is another really, and these significantly constrain its properties, but there's another really important property, which is a negative result, which is that we have been looking for the interactions of dark matter with other particles other than through gravity for many decades. And what we have for the moment is a large ensemble of null results. So that sets upper limits on how dark matter can interact with other particles. It interacts with them weakly or perhaps not at all, except by gravity. And these pieces of information together are enough to tell us that we cannot explain dark matter through any physics that we currently understand. Within the standard model, the best particle candidate might be the neutrino. It is electrically neutral, doesn't scatter efficiently with light, is stable, long-lived, so it could be the dark matter today, but neutrinos are light and fast-moving, too much so to make that filamentary web of dark matter, which is needed to support the formation of galaxies. So there are other sort of standard model adjacent possibilities, like maybe dark matter could be primordial black holes left over from the very early universe, but we would still need to explain where those primordial black holes come from. So I think this is a fair statement. Dark matter can't be explained by any physics we currently understand. Figuring out what it is thus a major challenge for fundamental physics. And the list of things we don't know is consequently much longer than the list of things we do know. We don't know what this stuff is made from. We don't know, are we talking about some kind of new particle or something macroscopic, like the primordial black holes I just mentioned? If we're talking about some kind of new particle physics, are we talking about one new particle or multiple new particles? 16% of the matter in the universe has a rich composition of different particles. Is 84% of the matter in the universe different? Does it interact with other particles except through gravity? Is it absolutely stable? It better be pretty long-lived or it wouldn't be there in the universe today to make halos around galaxies, but it could decay slowly over time. If so, what is the decay lifetime? We don't know the answer to that question either. Why is its abundance what it is? Where did this 84% number come from? This too is an open question. And perhaps of most interest to the particle physics in the room, is this connected to other deep problems in particle physics? Doesn't have to be, but it would be nice if it was. And I could keep on asking questions like this for quite a long time. There are a lot of things we don't know about dark matter. So when faced with a puzzle like this, particle theory, wearing my particle theorist hat, I will say particle theorists will tend to do things like this. So this is a slide from the previous snow mass community planning process that our community went through about 10 years ago, which was an attempt to do a non-exhaustive categorization of some possibilities for dark matter candidates and how they could connect to other problems in particle physics. I do not want you to read every word on this slide. So I'll tell you, first, like just how to read this slide in general, and then 3 things that you should take away from this slide. So how to read it in general is that everything within this red line is a class of scenarios for what dark matter could possibly be, and everything outside the red line is a broader class of physics beyond the standard model to which dark matter might be related. So dark matter could be related to whole new symmetries of our universe, such as supersymmetry. If our universe has more than the standard 3 space and 1 time dimensions, dark matter could be related to that. It could be related to puzzles associated with the Higgs sector, or outstanding problems in the theory describing the strong interactions of the standard model, if it's, for example, a QCD axion. It could have something to do with the neutrino sector. It could be some kind of heavy sterile neutrino. Dark matter could even be part of its own sector and experience forces that the standard model particles do not, in the same way that the standard model feels electromagnetism and dark matter does not. In which case it could be, our best key to an entire new sector of particles and forces. So there are many possibilities, but the 3 takeaway points are: 1, our problem is not that we lack ideas for what dark matter could be. There are lots of viable possibilities for dark matter. This is, in a sense, not a hard problem to solve, in the sense that this is not a case where we have a shortage of ideas for things that are perfectly viable candidates with reasonable particle physics that could work just fine. So that's the first thing. Problem, we have lots of ideas. Second point is that the payoff for a dark matter discovery could be really large. If explaining 84% of the matter in the universe isn't enough for you, this could also be a key to unlock lots of other puzzles in fundamental physics. Not guaranteed, but it is something that in part motivates me to try to figure out what this stuff is. But the third thing is that everything on this slide and things beyond this slide are currently consistent with observations, but probably at most one of them is the answer to what is the bulk of the dark matter in the universe. And it might be 0, right? So at the moment, the observations that we have are not sufficient to allow us to effectively distinguish between dark matter moles. They teach us some things, we can rule out some categories, but this is part of the motivation for searching for non-gravitational interactions of dark matter, that any positive detection of a non-gravitational interaction of dark matter would be extremely effective in excluding most or all of these possibilities. So given that, there are lots of different ways that we can search for dark matter, and in particular for dark matter interactions with visible particles. Not all searchers are looking for interactions of dark matter with visible particles. There are some things you can do without requiring such an interaction. You can look for signals of dark matter interacting with itself and changing its distribution. If dark matter is especially light or especially heavy, you may be able to get probes from looking at the structure of galaxies or gravitational lensing. But over a lot of parameter space, what you need to look for is some kind of indication of non-gravitational interactions with the standard model, which in many of the scenarios that I showed you are present at a level that we would hope to soon detect. So the classic classification of different searches for dark matter is to think in terms of taking a sort of schematic diagram of how dark matter might interact with known particles. So SM here stands for the standard model of particle physics, and chi is a standard symbol for the dark matter. And imagine sort of taking this diagram and turning it around. Yeah?
84% is the value today, right?
Yes.
But any idea what it used to be?
Good. Yeah, really good question. So our measurement of the abundance of dark matter comes from observations of the cosmic microwave background, which was released when the universe was about 400,000 years old. There are constraints on, so they start like, so there's the CMB measurement, gives us that 84% number, but then we have confirmations of that from looking at how structure formation occurs after the cosmic microwave background is released, all the way through to the present day. So there are constraints on how much the abundance, like purely gravitational constraints, nothing to do with standard model interactions, on how much the abundance of dark matter can have changed since the CMB was released when the universe was about 400,000 years old. And my recollection is that number is that the abundance should not have changed by more than 4% over that time. So 400,000 years old and today, we think it's pretty similar. Like there's not a lot of room for it to change. Before the universe was 400,000 years old, you've got a lot of freedom. If there was a huge amount more dark matter, you could potentially disrupt the expansion history of the universe at those early times. But when the universe was less than about 10,000 years old, it was completely dominated by radiation, and any matter component is expected to be pretty subdominant. So unless you actually have enough dark matter to overwhelm the radiation, there's probably like, you have a lot of freedom in what you can do there. There are constraints like from, well, there are not constraints at the moment. If there was a really early epoch where matter came to dominate the universe, whether it was the dark matter today or some other related component, there could be signatures of that in gravitational waves that could be visible in future experiments. The problem is that probing the universe before the CMB was released, like at that time, the universe was totally opaque to photons. So we can't rely on photons to give us information from those early epochs. We need to rely on other things like light element abundances, maybe in the future gravitational waves, maybe the neutrino background, if we can ever detect that. Does that help? But yeah, so like for almost all the last 14 billion years, the dark matter amount has been, we think, pretty constant. But once you go back to the really early universe, it could have changed a lot. And I'll actually give an example of how the dark matter abundance could have evolved, but it's just one example. We don't have good constraints. Okay, so back to my searches for dark matter. So the basic idea of indirect detection is that if dark matter particles were to collide with each other out in space, they could potentially produce standard model particles. And indirect detection could, like, this is drawn as a 2-to-2 interaction, but that doesn't have to be the case. If dark matter was unstable and decayed, then there would just be one dark matter particle in this initial state decaying to visible particles. But so the idea here is that you look for regions of high dark matter density and you search for standard model particles or their decay products produced through dark matter processes. And that's going to be the main focus of the searches that I talk about later in this colloquium. But we can also imagine looking for other signals. If you turn this diagram on its side, then you can imagine looking for standard model particles recoiling when a dark matter particle hits them and bounces off. This is, you know, kind of like looking at Brownian motion, looking at that tells you about what's happening subatomic scales. So this is done by building large underground, heavily shielded experiments and carefully monitoring standard model particles for jumps or recoils induced by dark matter passing through your detector. There's if you had this phenomenon, these scatterings were happening not inside your detector, but out in space, there are also some constraints on that from cosmology. Provided the scatterings actually happen within the detector, we call this direct detection because you would be directly seeing the effects of the dark matter interaction. And the sort of third rotation of this diagram is to say, if we could collide standard model particles together at high energy at colliders, this is how we've learned about lots of other particles, but among other things, they could produce dark matter particles. Now, because dark matter particles are definitely stable on the lifetime that it takes to get out of a collider, that in this case, you wouldn't be able to see the dark matter particles directly, but you could see their signatures potentially in missing energy and momentum from these collisions. Now, this isn't an exhaustive list. In recent years, there's also been a lot of attention to interaction terms like oscillations, that if you have an ultralight dark matter particle, it could actually convert into a photon in the presence of an external magnetic field in some scenarios, such as the axion. You could potentially have a situation where dark matter gets absorbed onto standard model particles, for example, as part of a scattering process like this that becomes an inelastic scattering process when looking for sufficiently light particles. So this is not exhaustive, but it's a convenient classification and a convenient way to think of different ways to think about the problem. And it also has a nice mnemonic, which I like, that you can think of it as you can either break the dark matter or shake up the standard model with dark matter or make a colliders. Okay. So within this landscape of searches for dark matter, you might ask, what kind of scenarios can we think about searching for? Under what circumstances might we expect to see a signal in these kinds of channels? And so now I want to tell you about like a general class of dark matter models that leads to nice predictions for signals in these channels, but then I'm going to show you a specific example of that. Now, this is a story about how dark matter got its abundance, but it's not a guarantee. There are other ways for dark matter to get its abundance in the present day, but this is one possible class of scenarios that has motivated a lot of searches. And that's the idea of thermal freeze out. So the story here is, let's suppose that something like the first process here, where dark matter particles can collide and make visible particles, was active, is a process that exists and was active in the early universe. When the early universe was much hotter and denser than it is today, this process, if it has a sufficiently high cross-section, would have been sufficient to keep the dark matter in thermal equilibrium with the standard model particles. What that means is that dark matter particles would collide to make visible particles would collide to make dark matter particles in the early universe, bring their abundances into equilibrium. So this here is a little cartoon of how the dark matter abundance would evolve in this case. At early times, when the temperature of the universe was hotter than the dark matter mass, there would be plenty of energy to make new dark matter particles. The dark matter would have abundance like any other radiation species. So the y-axis on this plot is the amount of dark matter per co-moving volume in the expanding universe. So in this phase one, we just have lots of dark matter, similar number of dark matter particles to photons. But then once the temperature, and the x-axis here is a time coordinate, but it's inversely proportional to the temperature of the universe. So as the temperature goes down, the time increases. But if this process was in effect, then when the temperature of the universe dropped below the mass energy of the dark matter, then dark matter production through standard model collisions would become inefficient, and the dark matter abundance would begin to fall exponentially at a rate governed by the rate of this annihilation process. So this would be phase two. And if we lived in a non-expanding universe, the dark matter would just annihilate away through this process, given enough time. But because we live in an expanding universe, there's another timescale in the problem, which is the timescale of cosmic expansion. And eventually this annihilation process would become inefficient relative to the cosmic expansion. Another way to say this is at some point, the dark matter is so rare that it's hard for a dark matter particle to find another dark matter particle and annihilate before the cosmic expansion pulls them apart. So at that point, we'd end up with a plateau in the dark matter density as shown by this phase three here. And the height of this plateau is just determined by how good the dark matter is at annihilating. If it annihilates efficiently, there'll be very little dark matter left. If it annihilates, inefficiently, there'll be lots of dark matter left. So if this happened in the early universe, which again is an if, we don't know the dark matter was ever in thermal equilibrium with the standard model, but if it ever was, then by measuring the amount of dark matter today, we can infer what the annihilation cross-section was. And yes, so to your previous question, there might have been a lot more dark matter in the early universe before this happened. So the required annihilation cross-section to match the abundance turns out to be almost independent of the dark matter mass. It comes in this number, which is about 2 × 10⁻26 centimeters cubed per second. If you put that in natural units, it's very roughly, there are some factors of a few here, but it's roughly the 1/100 TeV squared. And so if you say, all right, let's suppose I use my perturbative quantum field theory calculations and I ask what is the parametric size of this cross-section, I might expect the cross-section to go like some coupling squared divided by some mass scale squared. So if that coupling was comparable to our own fine structure constant in the standard model, which is around 10 to the minus 2, that would correspond to a mass scale associated with this interaction of about a TeV. So that's interesting. If we say, okay, you could get this right cross-section, you could get this correct cross-section with a mass scale around a TeV and an interaction strength around standard model electromagnetism, that points to the weak interactions of the standard model. So this is sometimes called so this scenario is called where dark matter is a weakly interacting massive particle, or WIMP, and this fact that the cross-section you need to get the right abundance is about what you would expect from a weak scale cross-section is sometimes called the WIMP miracle. Now, but note, the WIMP miracle doesn't actually say you must have the weak scale. If you had a significantly stronger coupling for the dark matter than standard model electromagnetism, you could go up to higher masses, up around the 100 TeV scale. On the contrary, if the dark matter is coupled much more weakly to whatever it annihilates to, you can go to lower masses. So this general picture is sometimes called thermal freeze out or thermal relic dark matter. It works pretty well for mass scales between about 1 MeV and 100 TeV within standard cosmology, and is sort of a simple predictive way of explaining how the dark matter might have gotten its abundance. But in particular, because this seems to pick out the weak scale, and we already had a priori reason for thinking there might be some interesting physics going on at the weak scale, there's been a lot of attention to try to probe this kind of scenario in the GeV to TeV mass range. So that GeV to TeV mass range has been studied really extensively, experimentally at this point. There is also lots of recent and ongoing work on the sub-GeV range, and increasingly also interest in pushing to higher masses. We have had no detection as yet of new weak scale physics at the LHC. We have also had no confirmed detection as yet of WIMPs or similar particles in direct or indirect dark matter searches. The direct searches are now probing really tiny cross-sections. The LZ collaboration recently released first results, and they're down to cross-sections of 6 × 10 to the minus 48 square centimeters, which are just absurdly tiny. These are, as far as I know, like the tiniest cross-sections we have ever measured in any context. Well, excluded in any context. It would be nice if we could measure them positively, but so you might ask a couple of questions here. All right, we've got all these great null results. Can we exclude, where we stand now, thermal freeze out as an origin for dark matter across this MeV to 100 TeV mass range? And if not, how close are we getting? And then we might ask, well, can we even exclude the more specific case where the dark matter is not just like in the weak scale mass, but actually interacts with the standard model through the W and Z bosons? So I will try to give you a sense of where we stand on the answers to these questions in the rest of this talk. So first, let's talk about the first one, just generically. I have this thermal relic dark matter, it annihilates away. I know what the annihilation cross-section should be because I know what I need to get the right dark matter abundance. Can we test that annihilation cross-section? So using our telescopes, we can search for the byproducts of dark matter annihilation in the present day universe. And this is the same process that set the original thermal relic abundance. So in some sense, it's the most model independent test of this scenario. There is a caveat. The conditions in the present day universe are pretty different than they were in the early universe. And so in some models, you can have cases where there's no more annihilation happening again. So those will survive, even if these constraints get very good. These are cases like where you have both dark matter and anti-dark matter, and all the anti-dark matter has annihilated away, or cases where the annihilation rate is suppressed at really low velocities. So there are some caveats to this, but we can still ask, all right, benchmark cross-section, if the annihilation cross-section is the same today as it was in the early universe, what would the signal look like? We also, we have stringent constraints from telescopes looking at our galactic halo of dark matter and beyond. There are also bounds over cosmological history that would tell us if we had like a spike of dark matter annihilation at an earlier time, and that are especially powerful for light dark matter. So this is from our recent snowmass process, a kind of summary sketch of where the constraints currently stand for dark matter annihilating into standard model particles, which then decay in a way producing photons. So y-axis here is the cross-section, or sigma v, which is the cross-section weighted by velocity, which is a figure of merit for all these searches. The x-axis is the dark matter mass. This is 10 GeV on the left-hand side, going up to 100 TeV here. This gray region, the 100 TeV, is where this scenario starts to break down for reasons just related to unitarity. And this orange line is this thermal freeze-out cross-section benchmark that I showed you earlier. So the pink region is the region that we are currently testing. These are two example channels, dark matter annihilating to B quarks and dark matter annihilating to gauge bosons. The answer is actually pretty similar for most channels, because if dark matter annihilates to quarks or anything that hadronizes, it tends to produce neutral pions, which decay making gamma rays, which is what these constraints are based on. If it annihilates to gauge bosons, they also decay, make a lot of gamma rays. So there is some dependence on exactly what standard model particle it annihilates to, but this general picture is actually pretty generic. So we see that at the moment, we sort of test this thermal relic benchmark for masses below around the 100 GeV scale. But we don't generally have a lot of access to this kind of thermal relic cross-section at hundreds of GeV and up. Now, with near-term telescopes, in particular proposed ground-based gamma ray telescopes such as the Cherenkov Telescope Array and the Southern Wide-Field Gamma Ray Observatory, this green line, sort of the forecast for what kinds of constraints we might be able to set over the next 10 years or so. So this is pretty exciting to me. If these telescopes are actually built and actually hit their design sensitivity goals, they will have the possibility to probe this thermal relic scenario up to almost the scale where it just starts becoming unviable for other reasons, because it's hard to build feasible models. So first, at the moment, we're probing scales below the weak scale, essentially. In the next decade, we'll be able to push almost the way up to the point where this scenario stops working, at least in standard cosmology. I'm not going to talk in detail about this, but as well as these constraints, there are also some puzzling excesses in the data, some things that we don't fully understand. They could be telling us about something about dark matter. It's highly likely that what they're actually telling us about is that we don't understand something about the astrophysical backgrounds. And so that's something we need to understand better. This is a nice white paper that was written as part of the SNOMAS process, summarizing the current puzzling excesses and paths towards resolving them. So, but that's a whole different colloquium. So I'll recommend that paper to you, and I'm happy to chat to people if they like. Now, I just want to say briefly before I get into my main example, that while I've talked about this as a way to probe thermal dark matter, it's not actually restricted to probing thermal dark matter. Here, we're just looking for any kind of dark matter physics that produces high energy particles, in this case gamma rays, coming from regions of high dark matter density. That is a fairly generic signature that can show up even in models that did not get their abundance through this thermal cross-section. The only thing that changes in that case is that this orange line benchmark is less relevant to you. In particular, if dark matter decays with a long lifetime and produces photons through its decay, this plot shows the limits that we can set on the lifetime of dark matter. Again, pink is current sensitivity, green is where we're going to go in the near term over the timescale of the next decade, blue is a far-term optimistic forecast for if we keep pushing beyond the next decade. This is also showing different final states. At the lowest masses, the only thing the dark matter could possibly decay to is photons or neutrinos, because those are the only things light enough. At higher masses, you could potentially decay to electrons and positrons, and then above about the GeV scale, you could start decaying to hadronic states. But the thing I want you to notice, which I know this is hard to see, so I'll just tell you, the bottom of this plot, this lifetime corresponds to about 10 to the 25 seconds, which is about 8 orders of magnitude longer than the age of the universe. And the x-axis here starts at the KeV scale and goes up to the Planck scale. So observations or non-observations of gamma rays and at lower energies, X-rays, coming from regions of high dark matter density are already allowing us to rule out any dark matter component that decays to anything visible with a lifetime that is much shorter than 8 orders of magnitude longer than the age of the universe. And in some cases, up to the Planck scale. And in some cases, our limits are much better. Like the upper bound here is about 10 to the 30 seconds, which is about 12 to 13 orders of magnitude longer than the age of the universe.
Raise a question.
Yep.
So being able to make these predictions requires that you have an idea about the densities of the dark matter and,
yes,
and the halo and stuff.
Yep.
There's astrophysical uncertainties there. Are you going to talk about how you think?
I'll talk about astrophysical uncertainties for the gamma rays from the inner galaxy a bit later. But yeah, that is certainly true. For decay, this is probably less of an issue than for annihilation, because for decay, what we care about is just the total amount of dark matter in the region, which is exactly what we measure from gravity. For annihilation, we care about the density squared, which is not exactly what we measure from gravity. So, okay, yes. So let me, and just as one example of the breadth of these decaying constraints, one thing that they can do is constrain that primordial black hole possibility that I mentioned earlier. So this plot is showing the, this first plot is just showing the sort of open window for primordial black holes to be all the dark matter. The y-axis is the fraction of the dark matter that could be in primordial black holes. The x-axis is the mass of the primordial black holes. There are a lot of constraints from here on here. Basically, the dashed ones are the ones that the author of this review thought were not very robust, which leads to this allowed window at a mass range of about 10 to the 17 to 10 to the 23 grams, which roughly corresponds to the masses of things in the asteroid belt. So these would not be black holes born from stars. These would need to be tiny black holes born in the very early universe. The thing that rules out black holes at higher masses is primarily gravitational lensing constraints. But at lower masses, the constraint is coming from exactly this kind of indirect detection search, that 10 to the 17 gram black holes would decay away through Hawking radiation, producing X-ray and soft gamma ray radiation. In that sense, they would be decaying dark matter. This second plot shows the constraints from gamma ray telescopes on this. The black and gray region is the region currently ruled out, partly by my own work a couple of years ago. And then these colored lines are showing what we could do again with gamma ray telescopes that are proposed to launch over the course of the next decades. This would allow us to search for black holes in a mass range. It would allow us to get up to a few times 10 to the 18 grams, so covering about an order of magnitude beyond what we can currently do. Okay, so my baseline statement for that is indirect searches and gamma rays in particular are powerful constraints that are broadly applicable to many dark matter models, including non-particle dark matter models, and which have the potential for huge advances over the next decade. But let's now go back to that question that I asked earlier about, can we kill like the simplest possible WIMP scenario? Like if I say dark matter that just interacts with the state. So I think I've probably told you, okay, at the moment, we can't kill the generic one. Maybe in 10 years, I'll come back and say, all right, we tested the thermal relic cross-section across its whole mass range. But at the moment, we can't do that. So can we do this? Can we exclude just dark matter that interacts with the standard model via the W and Z bosons? And the answer here is, well, I'll give you the spoiler. The answer here is, well, still not, but we're getting really close. So for this part of the talk, I'm now going to focus on another subset of dark matter models, which are in some sense to me like the sort of stupidest possible set of dark matter models that you would write down if you did it immediately after learning about the standard model. So like I've just learned about the standard model. I've learned there are these gauge groups, SU3 cross SU2 cross U1. And then I say, oh, there's another particle in the universe that I have to explain. What might I do? I might say, all right, let's put the new particles in some representation of the standard model gauge group and see what happens. So minimal dark matter says, right, let's just do this. We don't want the dark matter to have an electromagnetic charge, and we probably don't want it to be strongly interacting because we want it to have pretty weak interactions. So let's put dark matter in some multiplet of the standard model SU2 gauge group. If you don't know what the modes multiplet and representation mean in this context, don't worry about it. It just means that it interacts with the W and Z bosons of the standard model in predictable ways. So it's in a multiplet. So when I say it's in a multiplet, that means that there are other particles that interact with the dark matter and the W and Z bosons in the same way that electrons and neutrinos interact through the W and Z bosons. And the size of the representation just tells you how many particles there are in the multiplet. The dark matter itself has to be neutral, but the other particles in the multiplet can and generically will carry electric charge. That's going to be important later. So once this is true, once you have picked the representation that your dark matter is in, then the interactions with the W and Z bosons and with these partner particles in the multiplet are completely fixed by what representation of the standard model of weak interactions you picked. So this is an example of the triplet representation where, so triplet means there are 3 particles in it. There's the dark matter, and then there are 2 charged partners, which we'll call chi plus and chi minus. And the interactions of these particles are just given by these diagrams. Chi plus and chi minus are charged particles. That means they can radiate a photon or a Z boson. Or you can have an interaction that connects the neutral component, the dark matter, and the chi minus or the chi plus through emission of a W boson. Okay, like those are the only interactions you can have, and we know exactly how strong they are. Their strength is just governed by the weak interactions. Now, there's a free parameter in these models, which is how heavy are the particles in these multiplets. But the way that the dark matter gets its abundance is through this thermal freeze-out story that I told you about before. The mass of the dark matter governs how fast it annihilates. So if we know what annihilation cross-section we did in the early universe, we can reconstruct the dark matter mass from there. So then you have no free parameters. Your only free parameter is this discrete parameter that tells you what representation of SU2 am I in. So here are just like some examples of how we build those representations. There's the triplet that I already mentioned. This is also called the WENO, or the WENO, because it appears in models of supersymmetry where every particle has a superpartner as a superpartner of the W boson. As I said, 3 total particles. There's the dark matter. Its charged partners are a little bit heavier, and it will give you the correct abundance for dark matter if the mass of the dark matter is 3 TeV, roughly. I'm rounding everything to one significant figure here. Then we can go up to somewhat higher representations. There are other representations as well. I'm just going to use these examples here. The quintuplet representation has 5 total particles. It has the dark matter, and then charged partners, which are a little heavier, and doubly charged partners that are a little heavier again against the quintuplet because there are 5 of them. Now, for this case, you get the right dark matter abundance if the dark matter has a mass of 14 TeV. And we can keep on going, and we can keep on going like this. This plot on the right shows, well, it's going to show signals, but it's, these calculations have been done for, in this case, it's for multiplets with an odd number of particles, which has some advantages that I can talk about more if people are interested. So, and you can go up to potentially quite high representations. So then you can say, all right, these models are super predictive. They have no free parameters once you pick the representation. Like, you tell me how many particles are in the multiplet, you're done. But these models are actually really hard to exclude. So this plot up here is showing the expected cross-section of these models in direct detection experiments. So this is the scattering cross-section on the y-axis and the mass of the dark matter on the x-axis. And each of these little red and blue points corresponds to one of these minimal dark matter models. So they correspond to different representations, and blue versus red is whether the dark matter is a fermion or a scalar. The current constraints at the time this paper was written were this green region up here. LZ, which is the experiment that's just released its first results, this line is the ultimate reach of LZ. This yellow line down here is the ultimate reach of the next generation proposed big direct detection experiment, Darwin. And I don't know if you can see it, but below this, there is this gray region from Darwin, which is sometimes called the neutrino floor. This is when solar neutrinos actually become an irreducible background for your experiment. And the hope here is that over the next decade, we will get to the neutrino floor. So if we can do that, we will test all of these models. Like, they are testable. But at the moment, they're orders of magnitude away from being able to give a detectable signal in any of these experiments. So that's one way to test them. Like, wait for a decade, hope that we get to the neutrino floor, see if we found anything. But we can do something a little bit quicker. Let's see. For colliders, this is even harder because the high masses needed to explain the full relic density make these things really hard to go after at colliders. The LHC has a 14 TeV center of mass energy. This plot is showing the reach of a futuristic 30 TeV muon collider, which is one of the exciting ideas that came out of SNOMAS. This is for the quintuplet representation. These different lines are showing the reach of different searches, and they could get to masses between 5 and 10 TeV, which is amazing, one hand from the perspective of a collider, but it won't get you anything beyond this we know representation. So as you can see from the earlier part of my talk, of course, now I'm going to say, but indirect detection is the way that we will find these scenarios. So what kind of signals might you expect from these? So the dream signal is that 2 dark matter particles collide and they produce 2 gamma rays going out back to back, each carrying energy equal to the dark matter mass. So this is just like electrons and positrons annihilate into 2 photons. This is a dream signal because it would give you a gamma ray spectral line where you have many photons with identical energy, and there's basically no background for this at gamma ray energies. So this would be great. The only problem is that it's expected to be small. Dark matter is dark. It doesn't like to interact directly with photons. There are other signals as well. If the dark matter annihilates into any other standard model particles, most of those particles are unstable. They will decay. When they decay, they will make, as I talked about earlier, they can hadronize, they can decay, they can make photons. And so we can look for those photons. We can also look for lower energy charged particles coming out of those decays. So this is an example that will show up again briefly later in the talk of a forecast prediction for one of these models. And I'll go through how this forecast is done. So in this case, you see we have this line signal. The reason why it's not actually fully monochromatic is because the detector has some energy resolution at high masses. And then at lower energies, we have this bump of lower energy photons that are coming from production of unstable particles that subsequently decay. This black line is showing an estimate of what the astrophysical background is in this region. So you can see that, if you want to get at this bump of lower energy photons, it can be easy to confuse this with the background, and you need to, understand your background pretty well. And for the puzzling anomalies that I mentioned earlier, they're usually of that form, and understanding the background is very critical. But the line has a very distinctive shape, and if you could see it, you would actually be pretty convinced that there had to be some new physics going on. Okay, so yeah.
I'm going to see this throughout the universe at different redshifts. For everyone.
Great question. Yeah, so you would see this throughout the universe at different redshifts. There would be, and if the line was emitted early, it would be redshifted from there, so it would be a continuum. So there should be a signal in the extragalactic gamma ray background in this case. The thing is that we are living inside a pretty big concentration of dark matter, which is the dark matter halo of the Milky Way. So usually for annihilation, the prediction is that you will see the signal from our galaxy's halo before you see the signal from the rest of the universe. But it absolutely should be there, and that would be a confirmation that you could try to do. It's just a question of which is stronger. And for decay, I think often it's the other way around. Like, you expect to see the extragalactic signal before you necessarily see the galactic one. But it's just, we live in a very overdense region of dark matter, so that helps us. Okay, so if we want to predict these signals, what we need to do, we need to be able to predict the rate with which dark matter particles can collide and annihilate in our target region. We want to be able to predict the spectrum of particles that come out, and we're going to need to know about the dark matter density in our target region, as was asked about earlier. So for the moment, I'm just going to tell you about the theoretical challenges in computing everything but the dark matter density, and then I'll talk about the dark matter density uncertainties as we get towards the end. So the standard method for computing this first part of the problem is to use perturbative methods in quantum field theory. But there are a couple of issues that come up in minimal dark matter scenarios. I'm hoping I can go a little over time since we had the snafu with the saying yes to be recorded earlier. Okay, so the first issue in these scenarios is that it turns out that once your dark matter is like 3 TeV or heavier, then contrary to most of our intuitions, the weak interactions count as a long-range force in ways that I will explain. And you need to take those effects into account, and you can't always use standard perturbation theory. So let's talk about some of those non-perturbative effects. So one sort of basic format of a non-perturbative effect is, can I get bound states out of this system? So bound states are supported by stronger long-range potentials. If we think about the bound state that we all learn about first, which is the hydrogen atom. So in that case, there is an infinite range force, which is electromagnetism, which supports an infinite tower of bound states. So if we think about the potential, and okay, I haven't gone the 1/r potential properly, but if we think about the potential of the hydrogen atom, there are like deeply bound states, and then there's this successive tower of increasingly less bound states, this 1/n squared that we'll learn about in quantum mechanics. Now, if we have a massive force carrier, the force has a finite range, and that means that the potential has a finite width. That tends to reduce the number of bound states that are available. Some of you may have taught or taken quantum mechanics where you looked at the square well potential and you looked at making the square well narrower or shallower. You see the bound states move out of the spectrum as you do that. So the basic criterion to have bound states, and eventually if we make the potential short range enough, there won't be any bound states anymore, and we can treat the interactions perturbatively. So the basic criterion for bound states is that the bound state, the size of the bound state, which is given by the Bohr radius, should fit inside the range of the force that is mediating the bound state. So the range of the force is determined by the mass of the force carrier. So that essentially means that the mass of the force carrier should be less than the relevant coupling. So this is like the fine structure constant in EM, multiplied by the mass of the constituents of the bound state, or the reduced mass if they're of unequal masses. So, okay, so this tells us light force carriers are associated with bound states. light force carriers relative to the things making up the bound state are associated with bound states. So let's look at the weak gauge bosons. So the W and Z bosons are around 80 to 90 GeV in mass. The coupling strength of the weak interactions is around 1/30. We know this is all standard model stuff. So that suggests that we should have to worry about bound states if the bound state constituents have mass around 100 GeV divided by alpha weak, or 80 to 90 GeV divided by alpha weak. Again, I'm sort of rounding everything to one significant digit here. So that means that we're at the 3 TeV mass scale or heavier. We should worry about bound state formation. So they're basically everything on this plot is in the regime where bound states may matter. Now, these states generally won't be stable, unlike our hydrogen atom. If they'll be like positronium, which is an electron-positron bound state that can annihilate into photons. These dark matter particles can annihilate with each other, so the bound state can decay through that annihilation. But so this means that it's an effective extra contribution to the annihilation signal. Now, the presence of bound states is also a more general signal that if bound states are around, that means that the effects of this interaction are not perturbative when particles are going at low velocities, right? They can support a bound system. So that signals that the effects of the potential can be large and non-perturbative. Now, this only matters for particles that are going pretty slowly. One way to think about the parametrics is if the potential energy of the particles from the interaction is big compared to the kinetic energy of the particles, then these effects can come into play. If the particles are just speeding past each other and their kinetic energy is always much bigger than the potential energy, this won't matter. So that criterion is basically that the reduced mass of the particles, like mv squared, should be less than the energy associated with the potential, which is alpha squared times m. So this means that whenever you have velocities less than the relevant coupling, this will potentially come into play. The typical velocity of dark matter particles in our Milky Way halo is about 10 to the minus 3 times the speed of light. So if you have a coupling that's stronger than 10 to the minus 3, which the electroweak coupling is, these effects are going to be important in our halo. And this is a plot just showing how large these enhancement factors to annihilation can be. So this parameter is describing the mass of the force carrier, this parameter is describing the velocity, and this color bar goes up to 10 to the 4. So you can potentially get pretty large enhancements to the annihilation rate of these particles. This is all good news for us, like extra annihilation channels, more annihilation rate, this is all great. There's also an extra subtlety here, which is that in this particular case, the potential doesn't just enhance the overall annihilation rate, it can enhance particular final states. So in particular, in this case, it enhances the annihilation to our favorite signal, the gamma ray spectral line. So the reason for this, so yeah, the sort of the left panel, which is the explanation of people who've never seen Feynman diagrams before, and the right panel is for those of you who like Feynman diagrams. So the way to think about this qualitatively is when the dark matter particles get close to each other, the dark matter particles can effectively excite into their charged partner particles using the energy of the potential. Okay, so we can go like chi naught, come in, but when they get close to each other, some of the time they're in the chi plus, chi minus state. But if they're in the chi plus, chi minus state, chi plus, chi minus can annihilate straight to photons. That's no problem. This is just like charged electrons and positrons annihilating straight into photons. Charged particles love to talk to electromagnetism, right? It's just the dark matter doesn't. So what that means is that in that case, the presence of the potential not only beefs up the overall annihilation cross-section, because it gives you access to these charged partner states, it means that you can actually annihilate efficiently into a gamma ray line. So, and yeah, for those of you who like Feynman diagrams, the picture is this diagram isn't allowed because the dark matter doesn't talk directly to photons. Normally, you would expect that it would be a one-loop suppressed process like this, but in the presence of a long-range potential, ladder diagrams like this actually come to dominate over the tree-level diagrams. And at this point, there's no particular difference between the gamma-gamma final state and other final states. So we can actually have quite a large branching ratio. So MDM is great for indirect detection in multiple ways. It's good at making gamma ray lines. It typically has an enhanced annihilation rate, and it can make bound states as an extra annihilation channel. There's one more thing that we have to worry about, and then I'll get to the end and show you some results. So all the non-perturbative effects that we've talked about so far are things we know from quantum mechanics. We know about making bound states in quantum mechanics. We know about, we know that electrons and positrons annihilate better with each other at low velocities because they're attracted to each other, right? Like this is all familiar. And they can be studied using just using the Schrodinger equation for the initial state non-relativistic particles. But there are additional large corrections arising from infrared effects when we try to do the perturbative quantum field theory calculation. And these effects can be quite large. I learned about this when I wrote a paper on this in 2013, which kind of punted the issue. But this panel is showing where basically we did this calculation taking into account the long-range potential effects I've talked about, but saying that the final annihilation, the short-range interaction, was computed at tree level or one loop level. And normally you would expect these to be fairly similar to each other. You would expect the one loop correction to be small. But in fact, including the one loop correction reduced the overall cross-section by about a factor of 4 and a factor of 3 to 4. So this is an example and it turned out the reason was that the one loop diagram was really large and had the opposite sign to the leading order contribution. So when you added them to each other, they had a destructive interference, and the result was smaller by a factor of several. This plot is just showing like how big that correction gets from adding what should be a small perturbative correction to the original term, and you can see like here is like minus 40%. So then the question that came up then was, okay, what's this coming from? And if I had been working with Ian Moult and people like him at that time, they would have immediately told me, yep, we recognize this, we know what's going on here. This is associated with the radiation of low energy or highly collimated particles. It's associated with an infrared divergence in your theory. So the basic principle here is that if I'm thinking about final states that include a photon that are visible to telescopes, let's consider, like, for example, a final state which is two W bosons in a photon. This is not going to contribute to our line directly, but it's going to produce photons that we have to worry about. Now, when we do this calculation, we find that this diagram is proportional to the propagator associated with this part of the diagram. And that propagator has the following scaling, where EB and EC correspond to energies of the outgoing photon and the W boson, and theta here corresponds to the angle between two of these outgoing particles. And it turns out that this propagator, so here I am neglecting the W mass. I'm treating the W like a massless particle. Once I turn the W mass back on, I'm not going to get the same divergence that I'm just going to talk about, but I'll still get an enhancement, provided that the W is light. So the structure of this diagram is that I get a big enhancement in two circumstances, either where I'm radiating something that is very low energy, so where one of these energies go to 0, or where I'm radiating two particles that are extremely close together. And what's going on conceptually here is that if I'm just radiating off massless particles that have hardly any energy, how do I tell that? I can't necessarily distinguish that from a state that doesn't have those very low energy particles in it. Because, right, if they're actually 0 energy, they're not going to be detectable. Or if two particles are coming out extremely collimated and extremely close together, how am I going to tell that there are actually two particles there and not just one in my detector? So there are these physically indistinguishable states in the limit where everything is massless and where the energy goes to 0, the angle goes to 0, which lead to these non-physical infrared divergences in these diagrams. The way that they get cancelled out in that circumstance, they get cancelled out order by order in perturbation theory by taking into account that there's a corresponding infrared divergence in one loop diagrams with just a 2-particle final state. And they have to be combined because I can't tell the difference between the 2-particle state and the 3-particle state in this case. They're indistinguishable, they effectively add coherently. So now, of course, the W isn't massless. Like, the W has a mass. Once I turn on the mass of the W, these divergences are no longer infinities in my diagrams, and they have meaning. Like, I may be able to tell the difference between a state that has one, that has one W boson in it and one that has like W plus, W minus, W plus. I can count the number of Ws. So that regulates these infrared divergences. But a relic of it is that both kinds of diagrams, the 2-body and the 3-body diagrams, still have anomalously large contributions compared to what I might have expected. And parametrically, the way that this works is that they're enhanced by a factor that looks like the coupling times the log squared of the mass ratio between the dark matter mass and the W mass. So again, they would diverge as this ratio gets large. And so that means that we need to resum the logs for reliable results. This also tells us something else, which is that the 3-body final state is potentially going to be important. Like, if I radiate off, and it's not just the gamma coming out, I have to think about cases where there are 3 particles in the final state, but one of the photons is just below that line energy. So, and in that case, we have to worry about logs of another small scale as well, which is how far is the energy I'm looking at away from the endpoint of the spectrum where the line is. So this is the point where if I wanted, I or Ian could give a 1-hour technical seminar about what goes into the calculation. So rather than doing this, I am just going to tell you the very basic idea and then show you results. So the method that's used for dealing with this is soft collinear effective theory, which Ian is an expert on, knows more about than I do by a fair margin. So, the basic idea is that soft collinear effective theory focuses on identifying and treating properly these infrared degrees of freedom, the soft and collinear degrees of freedom, and allows you to do an alternative perturbative expansion to your usual perturbative expansion that behaves better in the limit where these logs are large, but the coupling is still rather small. So the recipe for putting together indirect signals for these channels turns out to be somewhat complicated. You need to solve the Schrodinger equation to determine the distortion of the wave function of the colliding particles and the spectrum of bound states in the theory. You can use the perturbation theory of quantum mechanics to compute the capture rate into bound states and the transition rate between bound states and the spectral lines from those transitions, and then use the techniques of soft collinear effective theory with this alternative perturbative expansion to work out the annihilation rate of both the unbound dark matter and all the metastable bound states and the spectrum of photons that you get from that. Now, having done all this work, it's worth noting that these methods are probably applicable beyond these simple models that I've been talking about. They're going to show up pretty generally whenever you've got a large mass hierarchy between the dark matter and the particles it interacts with. Like the presence of bound states, if you have light mediators, is generic. The presence of Sommerfeld enhancement is generic. The presence of infrared divergences in non-abelian theories is pretty generic. So a few years ago, we applied this approach to we know dark matter and found that current data from the Hess Gamma Ray Telescope should be able to exclude we know dark matter under somewhat conservative assumptions for the dark matter central density. So, and I'll tell you a little bit more about what that means in a couple of slides when I get to the new results, which are for quintuplet dark matter. And I'll tell you what we learned by doing that. So let me just give you a couple of little examples of what the output from this kind of calculation looks like. So if we want to look at, say, the bound state spectrum for we know dark matter, so the triplet dark matter in the limit where the dark matter mass is very heavy. This is not the bound state spectrum for we know dark matter. This is the bound state spectrum for the hydrogen atom. In we know dark matter, what happens is that some set of the energy levels effectively get displaced relative to the others, so that you now have a different spectrum of bound states and their decays compared to your intuition from hydrogen. Which states are metastable and the energy gaps between states are different compared to your intuition from hydrogen. And so if we could actually see the transition photons, which is a hard target, but maybe a far future target, we could actually do like dark matter spectroscopy on these models and learn quite a lot about their properties. Now, this is in the limit where we know like dark matter, where the triplet is really heavy, not at its thermal mass. At the thermal mass, it turns out for the we know there's one bound state in the spectrum, it's this ground state, and it doesn't contribute meaningfully to the signal. So you have to worry about Sommerfeld enhancement and you have to worry about the scared resummation, but you don't have to worry about bound states for the we know. For the scared resummation, this is from a paper from 2018 on which Ian was a lead author. This is the kind of formula that you get by doing the somewhat more complicated modified perturbative resummation of these large infrared divergences. These factors down here in the red block are the Sommerfeld factors that describe the effects of the long-range potential. Everything else here is describing how you deal with these infrared divergences and the result that you get. So it's a bit complicated, but you can also, I mean, there is an analytic expression that you can write down. So, okay. So that's the method. The one thing that I said we were going to skip over earlier and that we had to think about is the dark matter density profile. When you set limits here, you set limits on the photon flux. That means that the cross-section you constrain is degenerate with the amount of dark matter near the galactic center, and that has pretty large uncertainties. So simulations of dark matter suggest that the density should rise towards the galactic center, but possibly flatten out at some distance from the galactic center. This is a simplifying approximation, but this is broadly the behavior that we see. Now, unfortunately, the point at which the dark matter flattens out doesn't just depend on dark matter physics, it depends on what the ordinary matter, the baryons, are doing in the inner part of our galaxy. When I talk to current simulators, they tell me that in the Milky Way, we expect this core to be, it could be very small. You can't really resolve that from the simulations, but it shouldn't be much larger than about 1 to 2 kiloparsecs in the Milky Way. The distance from Earth to the galactic center is about 8.5 kiloparsecs. Now, a question that you might ask is, all right, so let's suppose that the dark matter density rises for another factor of few towards the galactic center, but then it flattens out completely. Can you kill that scenario if the dark matter is minimal dark matter? And how much sensitivity would you have if the dark matter potentially rises further? So this is just the cartoon of that distance from the galactic center. These lines are just showing the dark matter density flattening at different points towards the center. And then this lower plot is just showing how you would expect the actual signal from the galactic center to vary as a function of angle under these different core sizes. So it turned out that for the we know, the answer was yes, that if you had up to like a 2 kiloparsec core and we know dark matter with our detailed calculation, you should already be able to see it in data from the Hess gamma ray telescope. So that's sort of the level of the tension. Yes, you could maybe sustain we know dark matter as all the dark matter, but you would need the dark matter density to flatten quite a long way outwards from the galactic center at a level that seems to be in tension with simulations. So what happens for the quintuplet case? This is the 5-plet. So our SCET analysis, that complicated formula, it translates immediately, straightforwardly. We see no particular obstacles to extending that analysis to larger representations. But the bound states that were unimportant for the we know turn out to be important for the quintuplet. And we also have to take into account for the quintuplet that you could have actually charged bound states that involve both the dark matter and its charged partners and carry net charge in the halo. So we computed the formation and decay rate for each of those possible bound states. And so this is all in preliminary upcoming work, which would hopefully be out soon. And then we figured out what those bound states did, like how they decayed to lower states, what particles they produced in the process, and how they eventually annihilated away to visible particles. And these are the kind of results that we get. So this is the cross-section to make gamma ray Lion photons as a function of dark matter mass. The dashed line is the direct annihilation. The green line is the bound states. So even in this case, the bound states are probably a subdominant component. They do get important for more for higher representations. There are specific mass values where if you allow the mass to be a free parameter where the bound states are really important. But fortunately, at the thermal mass, it turns out that the bound states are still just not super important. They're not like basically zero, but in the we know case, but they tend to be pretty subdominant. So we can take all that, put that together and get a prediction for what the Lion signal would look like in something like Hess. And then we can go and confront that with, so this is not based on the newest Hess data because it's not public. This is using older Hess data to get an estimate of the exclusion. So this panel on the upper right is showing the expected theory prediction for the Lion signal. That's this blue line. This gray region is where you'd explain all the dark matter. And this yellow line is our predicted limit. So you can see the predicted limit is below the blue line. So that's good. That means that, we should be able to rule out the quintuplet. However, that's assuming that the dark matter density keeps rising all the way to the galactic center. That's not assuming like a 2 kpc core, like I just said. So this plot is showing like how large a core would you need to make the quintuplet consistent with the Hess gamma ray data. And at the thermal mass from this estimate, it looks like you would only need about a 500 parsec core for the quintuplet to be consistent with the data, which is probably fine. So the quintuplet, so we know is probably excluded. Quintuplet is right on the boundary of detection. If we don't see it in the next generation of gamma ray telescopes, it should be really dead. Okay, so thank you all for waiting. I'm sorry for going a bit over time, but yeah, so just to sum up, I hope I persuaded you that gamma rays provide a powerful probe of dark matter annihilation and decay across a broad mass range and a broad range of dark matter scenarios. I asked, can we exclude thermal WIMPs interacting through the W and Z bosons? And I say, we are getting actually pretty close to excluding thermal relic dark matter generically across its mass range. That's sort of next 10 to 15 years goal. But as we've shown here, there are simple models that still survive. And in this case, like they still survive despite a number of factors which cause your indirect detection signal to be larger than you might have expected. So these predictive SU2 models are not excluded by colliders or direct detection. Figuring out the indirect detection signals had some interesting theoretical implications and required us to build some tools which will hopefully be valuable for broader dark matter models. But when you do the detailed calculation, what you find essentially is the 3-plet's basically already ruled out. The quintuplet appears to be right at the edge of detectability at the moment. So, thanks very much.
So thank you very much for that wonderful talk. Are there any questions for Tracy?
Yeah, thank you. This goes back to the beginning of the talk.
Mhm.
And it's when the sort of the filamentary structure, the background where all the galaxies
Yeah.
follow today. Remember back in the 80s, there was a big program to try to calculate that on this observable mass of the universe, the mass of particles. You couldn't do it. So in fact, that background filamentary structure exists as an indication for the existence of dark matter. Now, the question is how do what goes in the model that predicts that? Somehow I would think that there has to be some sort of a dissipation or something that would go along with that, or is it just purely?
No, the model of dark matter that goes into simulations like this is dark matter is collisionless except by gravity and cold and slow moving. So you say it essentially has very little primordial velocity, and its only interactions with any other particle is through gravity. And that gets you this filamentary structure. Now, you can think about cases where dark matter does have some dissipative interaction or some self-interaction, and that can change the structure of dark matter, especially on small scales, like in these high-density regions where those interactions are more likely. And people think about what the observable signatures might be and how you would look for it. But to get that filamentary web, all you need is gravity.
So the constraints that you put on the minimal
Yeah.
model for dark matter assume that the charged dark matter particles decay into standard model photons.
Yeah.
Could you save the day for the minimal dark matter model by assuming that there's some decay into the dark sector photons?
Good. Yeah. So if you right. So in this example, like there are no, in this particular model, there are no dark sector photons. Like the only interactions are the standard model gauge bosons. But yeah, if you right. So more generally, if you want to introduce like other things for the dark matter to interact with, other particles for it to decay into, you can certainly So you can certainly hide annihilations in general in that way. But maybe not as much as you might naively think, right? Because at first you say, okay, this is fine. I want, like, suppose I'm not worried about like these minimal dark matter models, but I just want to think I want thermorelic dark matter. It's going to freeze out. I don't want to be ruled out by annihilation constraints. So then you might say, okay, I will do this by annihilating into something that we can't see. So like, I don't need to worry about these constraints if I'm annihilating solely into things we can't see. Great. But then you still have a question of what happens to the things that you annihilated into. Like if there is a dark photon bath that is sort of comparably abundant to the standard model bath, there are constraints on that just from cosmology, just from messing with the expansion history of the universe. If it's a lot colder than the standard model bath, then that's okay. But it will get heated up when the dark matter annihilates into it. So you need to make sure that you don't make too many of some relativistic species. If on the other hand, you say, okay, well, the dark photons aren't stable, I'm going to have them decay after some period of time, so I don't have to worry about their energy density, then you have to say what they decay into. So like there's a class of models where the dark matter annihilates into dark photons, but then the dark photons decay into standard model stuff. That doesn't help very much with evading these constraints unless the lifetime is like long compared to the age of the universe. And then you have to worry about the cosmological impacts of having this bath of dark photons sitting around. So like, yes, there are things you can do, but actually like adding a whole new bath of relativistic species to the universe kind of gets wedged in by cosmology on different fronts.
Are there any more questions for Tracy?
I have a question about this like Venn diagram of the landscape of particle physics model that you showed, which I really appreciated. You said that's sort of like the current status of how observation kind of tends to constrain different types of models.
Well, I mean, actually, this is a 10-year-old plot.
I realize. So my question is that what would it look like? How much progress has been made over the last decade? If you were to rewrite this now, like, could you just give us a sense of where we are and then where we are going in about a decade from now?
This basic picture of, so this is less about what is constrained and more about like general classes of dark matter scenarios. I don't think there are any general classes of dark matter scenarios that have been fully ruled out on this plot, that have been like fully ruled out over the last decade. And obviously like we don't have firm detection. So I can't like point to something on this plot and say, look, you know, this is the signal. I think that, I mean, right. So I would say that what's happened over the last decade is There is probably less enthusiasm for supersymmetry now than there was a decade ago, and that's partly because the LHC looked pretty hard for weak scale supersymmetry at the 100 GeV scale and didn't find it. That doesn't mean the supersymmetry is not there. The minimal dark matter models that I showed you can like easily be embedded in supersymmetric models. They're just at higher energies, which means they don't help as much with explaining why the Higgs boson is the mass that it is, which is one of the original key motivations for supersymmetry. But I mean, could still be there, could still be related to dark matter, just maybe not to the hierarchy problem. Another thing, like, I mean, on the other hand, there's a lot of enthusiasm and actually really, really cool experimental progress, some of which people here in this room are involved in looking for the QCD axion on this side of the page. And that's partly because advances in quantum sensor technology have allowed us to actually be able to probe the QCD axion. Whereas, so where we stand currently with the QCD axion, so this is a variant of a larger set of dark matter models, which are axion-like particles. The QCD axion is special because it could potentially explain what's called the strong CP problem in the strong interactions. And at the moment, our status is we have reached the ADMX experiment has reached sensitivity to the QCD axion across about a factor of 2 in mass. The plan for the next generation of experiments, which is like ADMX Next Gen and DM Radio, is to, and there are others as well. Those are the two that I have at the top of my head because they each will probe pretty wide regions of parameter space. Their plan over the next like 5 to 10 years is to probe something like 9 orders of magnitude in the mass of the QCD axion. So like, is the difference between less than half a decade and like 9 decades. And I mean, it's yet to be seen. They haven't built the experiment, so we need to see if they can actually do it. But that's a place where advances in sensor technology have really given us just like a qualitative difference in what we thought we could do a decade ago and what we think we can do now. In terms of new models, there's been a lot more attention to like fleshing out these possibilities that maybe dark matter is in its own dark sector that just talks to the standard model through some mediator and understanding what the implications of that would be. And I think the other thing that's new is people really thinking more seriously about heavy dark matter particles, like starting, you know, at energies where it's really hard to get to with colliders. So the MDM ones that I talked about are examples of models of that class, but you can go much beyond this. And I know that people here at Yale are working on like optomechanical sensors that have the possibility to measure very tiny dark matter interactions up to very high masses. And you can also do this with very high energy gamma rays and cosmic rays. So I mean, I think a lot of what's happened over the last decade is just people thinking more expansively about the theoretical possibilities, but recognizing that like we don't actually know what the dark matter is and there are a lot of possibilities. But at the same time, I think we also have better tools to go after very classic scenarios like the QCD axion or like WIMPs, like the minimal dark matter WIMPs that I talked about, which we can go at both with indirect and direct detection over the next decade.
Okay, so I think for time, we're going to have to wrap things up now, but let's all thank Tracy again for that great talk.